Thank you everyone for coming. I'll try to make it in the next 45 minutes talk about some use cases in the smart city situations. Now, even though the use cases will be in the context of smart cities, the same implementation can be done in other situations too. Let's say for your company, if you're trying to implement some image processing or classical machine learning techniques, and I'll talk about those. And covering an entire topic of smart city in 45 minutes, I think is going to be difficult. So I'm actually going to be going slow to start with, and eventually I'll start really running through some of the use cases. And if you have any questions, you can always interrupt me, and after the presentation we can still go for questions too. And second, I'm speaking English, and I'm not sure whether you guys have been listening to English presentations, and I apologize, I can't speak German, and you have to bear with me with my Indian accented English from California. Before we get into smart cities, and I want to really talk about, in AI nowadays it's almost like mathematics, and sometimes mathematics, even the application of mathematics, needs a little bit of a critical thinking. So I have a small riddle for you guys to start with. And it's not a smart cities thing, but maybe I think it's fun. On a Wednesday evening, you've been waiting and we had pizza. So just to refresh your brains, and I'll ask you a small riddle. Okay, you ready? Let's say a small girl goes to a store and she wants to buy a pencil. The pencil costs €5. She gives a €20 note to the shopkeeper, and the shopkeeper says fine, he gives a pencil, but he didn't have change for the 15 euros to give back. He goes to the next store to get some change, like he gets 4 5s. I don't know if 5s exist in euros or not, but listen, in the United States, in dollars, we don't have 5s. Anyway, so he gets 4 5s and gives 3 5s off to the girl and the pencil, and the girl goes away. After some time, storekeeper 2 comes to storekeeper 1 saying that, oh, this €20 note is a fake note. Storekeeper 1 says, oops, sorry, okay, I'll give you a different 20 note, which is a valid one. And storekeeper 2 goes away. Now the question is, how much money did storekeeper 1 lose? Yeah? 25, okay. Any other guesses? I'll tell you the answer, but again, this is just a fun thing so that it can talk about all of those. I'll talk about some of these use cases which are in bold text, and I cannot share the actual implementation in my company or my previous company, but actually I can talk about some of the published papers which were an inspiration for us. And what I do is, at the end of each slide, at the bottom of each slide, I have the link I provide where I've got the information from, and then you can, for additional information, you can always get that. Also, it's a good idea once in a while you can raise your hand, take a picture of the screen too. So keep your phones ready. The most critical and important part of a smart city implementation, even before you start thinking about AI, is the criticality of data. How you're going to get the data and how you're going to process the data. This is a paper published in 2017, September, just maybe less than a year ago, about what type of data that comes in. If you look into the architecture suggested, there are different types of network clients that's working, collecting data. You have streaming information that's coming in. Let's say if you have a social media, or if you have video cameras everywhere in the city, you have continuous video supply that's coming in. If you have audio sensors or any other types of sensors for traffic, let's say, you have that continuous information coming in, and you process that, and you can look at the picture in terms of the complexity of where you're going to store, how you're going to store, how you're going to extract, and how you're going to process this. So very, very complicated. There's a proposal published last year, and it's quite a popular one in terms of how data is being processed offline. Another common data point that comes in for your smart cities implementations is text. Now, if it's numbers, it's easy to do mathematical computations. Even if it's images, it's easier because every image has pixels, and each of the pixel has a pixel value, and then you can give the values or these numbers to the computer to process. Or let's say you want to predict the traffic situation based on the number of cars that's coming in, or predict the remaining life of a machine that's working in your company. All of these are based on numbers. But the complicated thing is when it comes to text. Either you have lots of documentation in your company, or you rely on information that's coming in as a continuous data pipeline. Let's say streaming media, or let's say you're watching for the sentiment analysis of, doing a sentiment analysis of your customers about your product. If you're a consumer electronic company, or if you're any B2C company, you really want to find out what customers are thinking. I remember 4 or 5 years ago when I was working for Apple, at that time Apple was trying to look for an implementation of sentiment analysis. At that time we couldn't find any reliable company because many times they were just doing word match and then find out what the sentiment is. But sometimes just by looking at the words, whether it's a positive word or a negative word, I think it's not. For example, the famous example of a sentiment analysis problem is sarcasm. You can't detect sarcasm in a tweet or a thing. 4 years ago that was a complication, 5 years ago, but now detecting sentiment in the entire message is so easy. I have written, I've open sourced 2 solutions for sentiment analysis. One for a small data set of 10,000 tweets, and there's another a large data set of 1.4 million tweets, and detecting sentiment in that. Do you know how many lines it took for me to write the sentiment analysis for this 10,000 tweets? If you are a programmer, can you predict how many lines it took? With the modern frameworks available today, I think I did it in 2016 or 2017. It was 23 lines of code. 23 lines of code for a bachelor's in computer science student, he or she can do it in, let's say, half an hour, 1 hour, maybe 2 hours, maybe just one day. You can do a sentiment analysis. And this model was 78% accurate, had 78% accuracy. The large data set, 1.4 million, it took almost 400 lines for me, out of which 300 lines was just processing the data. So actually the sentiment analysis model was only 400 lines. So we have come a long way in solving some of those problems, especially using text. But I really wanted to highlight here, when you have a text information that's coming in, it takes an extra gamble to process the data that comes in. And there are solutions available for that. And I want to really highlight when you have a data streaming architecture. I'll come to the real use cases in a minute, but the data streaming architecture. Let's say if you have a bunch of sensors from static devices, let's say traffic lights, and you also have sensors coming in from, let's say, automobiles or things moving, even human beings having a watch, or any other devices, let's say drones that's flying and giving out the sensor data. And you have that information coming in, first of all, before you start collecting it and providing that information to a bunch of servers, you've got to do a little bit of load balancing, and then all of this data has to be collated together, because if imagine a scenario which I'll talk about in a minute. There is a crime happening in one particular street, and people did not get a chance to call the cops yet. But people normally, something happens on the street nowadays, it's very common for people to take out and take a video of it. Maybe they are doing a live streaming, or they take a video and upload onto the Facebook account or whatever. There are models available that will process a video which is available in the public domain and identify, so you actually have a classification of an event happening in a video, and start plotting on a graph, on a map, and identify where this picture was taken, a video was taken. And if you have multiple individuals doing the same, taking pictures from different angles and different views, the model can still figure out that it's exactly the same scenario that's being filmed at the same location, and then can alert it. So you need to collate that information, so you actually put that into a bigger server, and you do 2 types of processing. One is some type of live responses that need to be given out. Let's say there's a traffic jam on a particular street, and then you have either cameras picking up or your other sensors picking up. You won't immediately respond to, let's say, a traffic jam or a medical emergency on the street. But if you want to find out, when do I need to relay this road? I think, Patrick, you will talk about the roads, I guess, after this presentation. When do I relay the road or repaint the road? that information doesn't have to be a live information. You actually can store some of it and then process it to see how many cars went on the street or how many vehicles and what's the weight of the vehicles, the rain and so many other conditions we looked into to decide when you want to relay the road. So you actually have a storage information, and then you also provide some third-party APIs. For example, you are a smart city and you implemented a smart city solution, and you have taken care of the, let's say, the crime part, and you really found out. But you want to give the traffic situation to a third-party company which is doing an analysis of, oh, does this city need a mass transit, an extra mass transit? That type of research can be done by third parties, so you actually can provide some APIs too. That's a very quick explanation of the infrastructure for implementing streaming data. Now, the reason I picked up this paper, of course, again published sometime early last year, is majority of the smart city implementations, you actually have streaming data that's coming in, whether it's textual or numeric or sometimes in video too. When I say video, I want to really explain the magnitude of it. A city of 1 million people can have anywhere in the range of 5 to 10,000 cameras, or it could be more too if it's a little more crime prone or congested city. But let's say 5 to 10,000, let's say 10,000. So every 1 hour, you're getting 10,000 hours worth of video that's coming in. Where would you store it? How would you even transmit it? Can you have a wired connection? Can you have a wireless connection? If you have a wireless connection, how much of bandwidth you need? So then comes the fog computing or edge computing, where you actually can do processing at the edge itself. I have one solution which talks about salient feature detection. Let's say there's a surveillance camera constantly watching. If there is a traffic congestion, it doesn't care, fine, it's going to store the information and keep it aside. But there is a crime that happens, let's say hit and run, or someone falls down. Then it takes that, processes the information right there, maybe take a timestamp t-10 or t+10 minutes of each side, or 5 minutes of each side, takes the video, takes a shot, and then sends it off for further processing. So that edge processing is coming, but in a smart city situation, one complication is the streaming data, the other complication is the amount of, especially the image data. And I just mentioned about 10,000 hours of video that's coming in, and you're talking about large-scale video management. How do you store it? 5 years ago, 3 years ago, there was a brute force implementation of storing all the video, because you never know what you need at a later stage, and also for legal purposes. I don't know about Europe or German legalities, but in the United States, you need to keep information for 7 years to really get out of the legal problems. Otherwise, you just store it for 7 years. You can't keep information like that. So there are image processing solutions which are called two-stream architectures, where the two CNN architectures processing the same video. One is only looking at the optical flow. That means if a car is moving, it looks at each frame and understands the flow of the object and then does a classification of it. What is happening? The action classification. Whereas the other CNN architecture would actually detect the objects in it. It's a car. So the first CNN architecture detects there is something moving, and the second says there's a car in it. So car moving as an action could be detected by these two-stream media, and this is what is happening here. In this way, you can do two-stream. Also, there is in this paper they mentioned this just only 4 or 5 months ago. 1712 is year and the month. They also suggest what type of standards you can develop for the edge computing, so that you can do some of the computing at the edge devices. Now, this paper has additional benefits. These are some of the most common use cases in a smart city. You can detect a human being and detect a car. Now, detecting a human being is a little complicated than regular human face detection. Let's say you have a Facebook account. You guys have Facebook accounts? Yeah? No. Yeah, that's what I thought, yeah. If you have already given your picture to your account, and you put it in your account, so Facebook knows who you are, can match your name with the face. Next time your face appears in any other picture from any on your friend's Even if you're not friend, let's say accounts come up into the Facebook account, it can immediately detect, and it can start automatically tagging it. Now that was a difficult problem 2 years ago, but now it's a solved problem. Why? Because the model actually has seen a standard picture. Many times it's a very, very clear picture of you. If you want to upload your profile picture, it has to be really pretty and nice and clear, right? You don't want to put a blurred image. So the model has seen a very clear picture of you. And now any other situations you have a picture that's coming in, it can detect. But here is the complication in a smart city situation. If you have a city of citizens, let's say 1 million people, unless there is an absence of democracy, you can't force everyone to submit their pictures to the government. So you have a scenario, let's say, you have 10,000 cameras. There's a camera number 1, 2, 3 on this street, looks at a person at 7 a.m. and there's another camera on a different street, number 5, 6, 7, looks at a different person on a different day and a different time, and now you have to tell whether these two people are same. Typically cameras are up 10, 15 feet away from the ground, so typically they have only a top view. Number one. Number two, if it is 2 different dates, there's every chance that the person is wearing a different type of clothes. Maybe they have shaved the beard or whatever. You have very small area on your face, and maybe it's called gait, the posture. That very limited information you get from these 2 cameras, and still have a process to identify whether these 2 are the same people. That's the complication of face detection using in a smart city implementation. Similarly, even vehicle identification. You think, oh, we can just get the number plate and then we can identify the vehicle. But sometimes it's blurry. You can't even you can't find the number plate of a car. What if the number plate is fake? You can't just rely on the number plate. But you want to find out, is the car which hit a person here and ran away the same car which was driven the next day? Yeah, you can look for scratches, you can look for dents, you can look for any color. What if there was no dent, there was no color? All of these unique scenarios, it becomes more and more difficult to detect a car. So face re-ID, vehicle re-ID are 2 complicated use cases, which there are models available, but they're not really very high accurate models. Maybe I think 80, 90% accurate, but not 100% accurate. Someone told me, it's a rumor, could be, Walmart was predicting the future revenues not only by using their supply chain demand and other stuff, because you have a real robust supply chain and people coming in and buying, you have an automated stuff, but also by looking at the number of cars that's parked in their parking lots. So this is an aerial shot of a parking lot, and it has to detect where is a car and of course count the number of cars. Now, sometimes I think if the picture is high resolution picture and if you're taken not too far away from this earth, maybe you can really distinctly identify from a naked eye, but sometimes it's not. And also, you see some of these rooftop objects, they may look like, and my model does not know this is rooftop and hence they may not be cars. Or you can have cars on a rooftop too, isn't it? If you have a big parking lot, you can have cars on the rooftop too. So, identifying whether this is a car or this is a car, and also how many pixels this has. If this whole image is, let's say, 1,000 by 1,000 pixels, now let's say 10,000 by 10,000 pixels. But this will be hardly any, maybe 100 by 100 or 50 by 50 or sometimes 20 by 20 size. Let me look for an example of even a smaller car. This looks like a small car because it's partially blocked by a tree. So you actually have a car there, you can only see the tail portion of the car. That portion is even smaller. Having a model detect a car was of course complicated, but it's very easy. This is the convolutional neural network model, and if you guys don't know what CNNs are, I can explain what it is, but there's a very, very simple, straightforward, multi-layer CNN architecture implemented, you'll find out what it is. And of course, they also used YOLO. Have you heard of YOLO? What does YOLO stand for? There's a very nice way of what it stands for, and there's an AI explanation too. You only look once. So the implementation here is you only look once and detect immediately. So YOLO 1 had come, then YOLO 2 came, and the YOLO 3 recently came. YOLO 1 was a little slow. It only could process around 40 frames per second. The initial objective of YOLO was to be used in autonomous cars, and you can't have a model which only can process 40 frames per second, because if you're going at 60 miles per hour, or in, let's say, in autobahns here, I drove today 160 kilometers per hour. On 160 kilometers, you can't actually have a model which is detecting frames at the rate of 40 per second, and hence YOLO 2K, which actually can process at 220 frames per second. But this is very a nice implementation, and this is an advanced implementation than the regular CNN architecture, where instead of just looking at the entire image and looking at every pixel, every corner of the image, they said, okay, let's draw a few boxes and see if this box captures the person. Let's say you have a picture of a bicycle and a dog, and you're training the model only to find out where the dog is. And the dog, right now of course the dog is here, but what if in a different image the dog could be here or here or here, anywhere. So it starts randomly drawing something called bounding boxes, and then detects whether the bounding box captured the object, or the person, the object you're looking for. They started with, I think, there's a first model called RCNN, Region Convolutional Neural Network. They started using around 2,000 bounding boxes per image. It used to take a long time. These people, I think, eventually come out with, I think, around less than 10 bounding boxes, and the model is really accurate too. And they've implemented this model even on a mobile device, so you actually can download. It is available online. You can download it to your cell phone and then sit in your car, let someone else drive, but you can hold the phone up and like this and keep on facing at the traffic. It will start picking the video, and then you see the video what you see with the naked eye, and it starts identifying a car or a person going in a bike or a tree or a person standing on the side of the road. It starts detecting. Even if you're driving very fast, it can detect. So if you have not heard of YOLO, I think you should play with YOLO. I picked a different example of a traffic detection, but not using video processing. It's more of a signals using just a bunch of sensors. So you actually can have 3 sensors on each side, and then identifying the disturbance in the signal, including the phase and the amplitude impact and the duration of the disturbance in the signal, could be used for processing and identifying and classifying vehicles. This paper was published as recently as January of 2018. They actually had a very high accuracy, and this is not even using image processing. So the traditional thought process that you can use image processing to detect traffic, they violated that, and they actually use sensors, which were actually faster, because images are too difficult to actually process. It takes more time to process than just a sensor did that. Okay. Yeah. If you want any further questions, you can look at the paper, or if you want any questions, you can ask me right now too. This is a little deep implementation, as is in Feb of 2018, about taxi demand prediction. And this is important in the context of, I don't know, do you have Uber in Germany? Ubers or Lyfts? No, you don't. So if you have these autonomous taxi hailing systems, they have almost similar models, slightly modified of course, but they have similar models to predict the demand for taxis and stuff. How much time? I think.
Just checking the camera.
Okay. I thought you were checking the time in there.
No.
Okay. Here, the taxi demand, they're using a small pixel image. It's almost, I think, 7 by 7 pixels. In my opinion, CNN models are not effective if the image quality is less than, I don't know, 12 or 16 by 16 pixels. This implementation seems to have done a decent job there, but I still don't believe that you can get any better. So if you implement a smart city solution, or implement, let's say, in your company, some sort of image processing. You guys are here today, so I'm sure you're all enthusiastic about AI. So here is a small use case you can do to impress your manager, and then get a promotion or a whatever salary hike and stuff. If you have a badge access into your building, or open the doors, or let's say to your apartment complex, see if you can implement a face recognition application for those 10 people. You can just get the application, run it on your cloud, then deploy it on your phone, put the phone, or maybe have a small cheap camera there outside, and then the moment the person walks in, you can have a display which actually shows whoever walks in, whether the person known person or not. It It'll be a very smart and cute thing, and maybe you can do it for your company, or maybe you can do it for your apartment complex where you live, or if you have a kid who goes to school, and then maybe you can show it in their school and the teachers will get really impressed. This will be a cool implementation that may get some bonus or salary. I talked about salient objects. In a smart city, even though there are models available that can predict whether it's an animal or a human being or a car or a vehicle, sometimes the city doesn't care all of those things. The city wants to know, was there a human being on that particular day? Because this is an unauthorized building, we don't want a human being. Maybe there's a dog or a bird coming in, we don't care. Or let's say this street should not have any cars, bicycles are fine, people are fine, we don't care for any other. So if you pick only a few salient objects, there's a few items you want to detect, it's a lot more easier to implement it, and the response rate is also very, very high. It's a very quick implementation. You can see in this picture you have two human beings and an aircraft, and using a technique called semantic segmentation, it actually can identify the profile lines of a human being and a profile line of an aircraft, and then it actually can even detect what object it is too. So this is implemented in a few places, again published I think in a conference called CVPR in 2017. You can have a less effective but very efficient model which only can detect a few objects, but that's very fast and doesn't take too much of a footprint on the devices. This is actually a second paper than what I wanted to actually share with you. In a face re-identification scenario where the model has never seen the original face, the way you train the model is you show the picture of a person, show this picture of the same person but a different picture, and give another picture of a person who is very, very dissimilar. And it's a different person. And you train the CNN architecture saying, okay, picture 1 and picture 2 are the same people, even though they look slightly different, they're wearing different dresses and different postures and different angles. And picture 3 is entirely different person. And if you start training the model, let's say a few, maybe 10,000, maybe 100,000 or even a million, model starts figuring out the intelligence on what to look for, even though there are two different pictures, but if it's the same person, it starts identifying what area should I focus to know whether this person or this person are the same or not. And then also knows what areas I should ignore by looking at the third person. That's called triplicate loss. So you actually can define a loss statement based on comparison of 3 different pictures. That was actually quite popular approach even until maybe a year ago. And the same approach was used even in news recommendation engine. Let's say you are developing a recommendation engine for recommending news. Problem with the news situation is, let's say there is an evolving story. Let's say like Christian, you said about there's a train, there's delays in train. And if that runs for, let's say, 3 or 4 hours. So the first 1 hour, maybe there's one news report that comes out, maybe another hour later there's another report comes out, which is more of an additional information from the same story. It's called evolving story. Or let me give a different example of the incident that happened in Thailand about those kids getting stuck in a cave. Have you heard of that? So there were 10, 15 young boys got stuck in a cave, and that collapsed because of heavy rains, and they were starving, and with their coach, and the whole international community was trying to help dig up that area to get those kids, and now because they are safe. After 9 days they were safe. But imagine on the day 1 or day 2 or day 3, when the news reports are publishing about the incident, what happened. It's the same story, but it's an evolving story. So identifying an exactly same 2 stories, or identifying a story but an evolving story, that is, which is actually additional story, it's a little more complicated problem. And in that scenario too, you can use a concept called triplicate loss. So after the triplicate loss became popular, there's another model that came out called quadruplet loss. So you're actually giving an additional picture to the model for it to learn a little more efficiently. So apparently in this paper, which was published again in 2017, they found that the model learns faster than the previous one. You don't need to actually show so many images of in the ground truth. Now, does that mean that you can do pentaple loss or 6 losses and 7 losses? We don't know. That's going to be. It's difficult to find 3 similar images of the same person as a data set, and I'm not sure it's going to work that way. This is another paper that was published. It's again last year, 2017, April. Just the same approach, but here they clearly distinguished between a closed set and an open set. Closed set is where the model has seen the photo or the picture of that person at least once, and hence there is a connecting tag for a picture to a name, and then you're looking at the same picture, same person, but a different picture, and then you can tag. That's called a closed set. And an open set is the one what I explained earlier. In a city, you don't know about every citizen, especially if citizens are coming outside the tourist place, you just don't know who are the people. And then it goes different. I think I'll skip this. This was the example I was talking about. When if you have an event happening in a street or in a place, and if you have your regular smart city implementation fails, you can rely upon the social media information that's coming in. You can process the videos. And the reason this is different is that these videos are being uploaded by different cameras and different resolutions, different pixel value, and all of that information, and having a model that actually looks at all the videos, even though from it's the same incident, but from different angles and different view and different clarity, model runs very effectively and then puts it on a map. That's another quick, again, this is just June of last year. That was a marathon run in a 100 meters dash, where I explained all the smart city implementation in 45 minutes. And as I mentioned earlier to you, that I think I will not be able to explain each and every detail, but I wanted to intentionally leave some time so that if you have any questions, I'll be able to, any of these presentations, I can answer the questions. And if you have any further questions, actually, I do have I've written a few blogs in AI, and I have a YouTube channel about all about AI. I've given tutorials on some of the AI topics, etc. If you are curious, you can go check that. But I'll be happy if you have any questions. Well, there can be 2 reasons why you don't have any questions. One reason is I was so brilliant, I was so smart, I was so intelligent, and you didn't have any questions. The other reason can be I was, you can guess what the other reason is. I was so ineffective in communicating what I wanted to answer to everybody. Christian, thank you.
The other reason was I was always thinking about telling you how much money, but did you already answer that?
Oh, that riddle? Oh, that's good. You remember that? Okay.
So I couldn't follow your whole session because I was thinking about that.
Oh, that's a good blame. Yeah.
So I pay 20 to get 20, but I give 15 away. Unfortunately, another 5 is not. Unfortunately, another 5 is not full, but I have maybe bought the pen for 2.
Just give me the answer up, and then we'll figure out.
15 plus the pen that I bought, so 17 maybe.
No, the pen was $5, about €5.
I bought the pen from somewhere else.
Oh, well, let's say there is no, the shopkeeper is just selling it 20, okay,
Yeah.
okay. So you said 25 plus pencil, and you said I think 25?
35.
35, okay. Anyone else? Any other answer? 20? Sorry?
For $20 real, but not for expensive.
Okay. What is the final answer? 20, okay. Yeah, the answer is 20. And there are 2 ways of finding out what the right answer is. One way of looking at it is ignore the existence of shopkeeper 2. The shopkeeper 2 was introduced only to confuse you people. So take the shopkeeper off, because the shopkeeper 2 was not doing anything. And now look back at the transactions. Then it becomes very easy to find out how much is the loss. Another way of looking at the same thing is make an assumption that there was no fake note. Are all the transactions valid? Yeah? And then go back to the assumption now. So you made the assumption that there's no fake note, and there's a 20 is a fake note, and shopkeeper 1 has the 20. So anyway, that's That's a question. By the way, even I do not know the answer when I have heard it for the first time. So, yeah.
I have a question to smart cities. So how do cities actually approach someone like you or a company like yours to get solutions? Do they actually know that a person like you can give them these solutions, or where do they find these solutions?
People don't come to me for that. My company does not even do smart city. Well, we do a little bit of something called safety and infrastructure. We have done some portions of it. But let me answer your question in a generic way. When the city wants to do smart city implementations, they normally pick one of the low-hanging fruits or low-hanging use cases that can be implemented in a smart city. The most commonly implemented smart city implementation is having a chatbot. So the city has a website, and there's a chatbot, and you can ask a question. Let's say you get your medical benefits or social security benefits, your tax information, or property related information. If you have any questions, you start typing instead of going to the city office or calling the city office. You can start typing, and then you'll get the information. And the next step is maybe audio-enabled chatbot, where instead of you going to the city, just pick up the phone, and then the audio chatbot can answer your question. That's the most common thing. The next most common thing many cities want to implement is because of traffic congestion or crime. If it's a really high crime, then they do it. Otherwise, it's always traffic, because cities are growing constantly. And if the mere fact that some city is thinking about smart city implementation, that means there is a huge influx of people coming to the city, because eventually the city administration also becomes intelligent to say, okay, let's start thinking intelligent and using technology. So typically traffic is one they would want to. So they actually have sensors everywhere, and then figure out where there's a huge traffic, and can we synchronize the traffic lights in such a way that we actually have smooth flow of traffic. Or let's say you have public transport of buses and trains, and on top you have people using bicycles and cars. How can we make sure all of these work together? There are big companies like Baidu has implemented some smart city implementations. They actually have it, I think, in a Malaysian city, and they also have it in some Chinese city. I don't remember the names. That's common. Even Google is working on that of smart cities, but they have different use cases. So every city has different use cases. Like I talked about gunshot detection. Some cities in US actually, where there's high crime, they only wanted to implement that, because that's one of the problems they want, and also because lack of funding is another issue too. But the famous companies are these 2 or 3 known worldwide, but there's a lot of other small companies developing a couple of use cases for smart cities. Remember, I think when you implement a smart city solution, it's a huge infrastructure cost. That's like your cameras and the online, the cloud storage and computing power it's a little bit of that. So they always go for some of the simple, cheapest ones, like chatbot is one, and maybe you can have radio sensors, if not video cameras, on places where to detect traffic and things. Yes, sir.
So, for this example of the responses, how it requires a lot of effort and probably infrastructure. But what could be best ideas in this field for the startups, like kind of 2 or 3 people coming together?
There's a fantastic use case for a startup company to make a lot of money is toll detection. Right now, I don't know, in Germany, maybe every vehicle pays the same amount of toll, but many of the developing countries in Asia and Africa, the toll you pay, the tax you pay, is dependent on what type of vehicle you're driving. And detecting what vehicle it is and deducting the right amount of money is a huge headache for the city government, because then you actually have manual people sitting there, and then you're collecting money and all of that stuff. And there are 2D image processing models for 2D and 3D, which actually can detect what type of vehicle it is, and that it's a very easy implementation available, and that could be a good starting point for a startup company trying to do with a couple of people to try to do a smart city. Another one is you actually can, if you can do a good face recognition, like I talked about, face re-identification, there are data sets available online for free. So you can train a model. Actually, some people have trained the models and kept it for free. You can take it out. And maybe you can go implement it just in one street and see if the city government wants to pay for that. And that would be a good example, a good maybe success story to actually spread it other places. But many cities have the following problem. One is there are too many calls that come to the city administration office. So can we address those calls? In other words, by having a chatbot or a voice-activated chatbot or a typed chatbot. Second is, so that's the one, if you have medical facilities to be addressed or tax information. Second is crime and traffic. If you can solve any of those cases using, but again, you may all think, oh my God, I need to develop a new AI model. If you search hard, there would be an implementation available for free. You can start that instead of starting from scratch. You can actually start taking that and then fine-tuning it. Yeah, Christian.
And where are we now concerning the quality of algorithms? Are we still advancing, like every 2 years they will double the capability of algorithms, or are we already stable and we just think about new cases of how to implement those?
In some areas, they're doubling on a monthly basis, or even once in a quarterly basis too. I'll give an example. To detect or localize and detect an object in an image, people used to use regular CNNs. And I think July of 2016, there was a technique called RCNN was invented, and people publicized it, and it was really fast. The YOLO image I was showing of that dog in that. So this blocks or regions, these two, the blue box and the yellow box, that's called regions. So you actually look in certain regions of the picture to find if there is an object here. That's called region convolutional neural network. That was proposed in July of 2016. And I think sometime in October of 2016, within 4 or 5 months, there's a new model called fast RCNN came, which was a lot more efficient and effective. And then sometime in March, April of the next year, another 6 to 8 months later, faster RCNN was invented. Engineers are not very creative in giving nice names. So anyway, so yeah, faster RCNN came, and that was very popular. But now there's something called mask RCNN, which is extremely popular, which is very, very efficient in detecting an object, multiple objects in a picture. So if you have two dogs and 3 cars and 2 people walking, there's an area of study called visual question answering. So you look at an image and you type a question. How many people are there? The model will look at the image, understand what it is. First of all, understand your question. Look for information in an image, understand the image, and answer the question back in text for you. So it's called visual question answering. Let's say you see a traffic light red, you can actually type and say, is it traffic light red or green? Look at the image and say, yes, red or green. Which is, that use case could be in somewhere in autonomous cars or any other implementations too. So that was the amount of leaps that just that particular image processing was taking. Natural language processing, 4 or 5 years ago, it was so difficult to convert text into numbers. So there was a technique called one-hot vectors. So you replace all the words with zeros, and one of the word, whichever you want to create the vector for, you look at the position of that word and replace that 0 with a 1, and that becomes a vector for that word. And that was effective for a long time. But now there are techniques called word-to-vec or GLOV, global vectors, shortened to GLOV. These are very, very, very effective techniques. Within 2 years, they become so dramatically different now. And that was for words, to convert word into a vector. Now there are methods to convert a sentence into a vector, a paragraph into a vector, an entire document to a vector. I have a slide, I think, in a different presentation, where if you look at all the articles written in Wikipedia and convert each of the article into a dot, into a vector, and then convert the vector into a dot, you can actually post it on a 100-dimension graph, and if you extrapolate that into a 2-dimensional image, you actually can see the dots, and each dot is named what is the dot refers to. And the interesting thing is, all the articles related to sports, all the articles related to politics, etc., those dots all fall together to each other. Means that the conversion of these articles into a vector, it's also capturing the essence and the meaning of the article. So I don't know when it's going to end, but this is really taking leaps and bounds. I think it's a good point. Maybe I should come out with a theory that AI models are leaping other, maybe they call it a S-case theory. It's a good suggestion. I think we have another speaker too. I don't want to take the time. Yes.
I don't know if it's right. It's an ethical question. You talked about crime prevention, and I heard that Stuttgart, for example, is using kind of machine inputs used in the US as well, but to prevent crime in certain areas. So before it happens, police
I don't. I know that there's a Tom Cruise's movie on that exact same topic. I haven't heard of that instance. What you're explaining, it's a possibility that it might have happened. AI is opening up so many top questions. Ethical, moral questions are definitely. Even before you go to a deeper topic like an ethical or moral question, there is another topic which can be easily addressed, and that's called the human bias that goes into a model. And here is an example for that. There was a job recommendation model that was recommending jobs to people. Let's say you log in and then say, oh, I'm an MBA and this and that, and it'll say, oh, you should try this job and this job and this job. After some time, the owners of that model, the company which created it, found that all the CEO job recommendations are only being given to men and not to women. Even though the model was never told explicitly that it's a gender-based job. And there were qualified women candidates too. But the problem is, and the model was not making any mistake. Model was given a data where historically, of course, the data was more men and less women. And model thought, oh, among other features, gender could be a reason why CEOs are only men. And after that, when you ask the model to start recommending the jobs, it says, oh, this person is a female, so obviously not qualified, even though other qualifications are there. So that's a human bias which sometimes I think AI engineers don't really pay attention to. I don't know whether you know this fact or not. There are 170 known biases. So we all have at least 170 biases. I can give you a few names. I won't explain what it is. Which I like it very much. You should go and research about this, called Dunning and Kruger effect. D-U-N-N-I-N-G and Kruger, K-R-U-G-E-R, Kruger effect. You'll smile to yourself what that bias means. So biases need to be also looked at. Okay, with that, thank you very much. I appreciate your time and